Ramki has made in the mathematical development of India. According to the Type 3 Upanishad, life is meant for two activities: to study and to teach. Swachaya pravachanabhyam prabhaditavyam. Do not refer.
No, his line got cut.
Oh, I thought that my line was the problem. So maybe his line.
No, his line was back.
Sir, you got cut. Can you?
Anyway, you are muted also.
Sir, yeah. We lost your.
Hello, sir.
Can you hear me now?
Yeah.
Yes.
You have to share screen again.
I actually don't know how to do that. Are you able to see that? No?
No, just share screen again.
Or share screen again. Is anything happening?
Yes.
Yeah, now it is there.
Now we can make it the full
Okay,
screen
and
mode.
did you want me to put that in full screen mode again?
Yes.
Okay.
Okay. Can you see now?
Yes.
Are you able to see?
Yes. Yes. Yes.
Okay. So as I was mentioning, I can see 6 of Ramki learned that he had 10, but so you have Senthil Kumar, Jaban Meher, Brindavan, Sahu, Karamdev, Shauli, and Kalyan, as far as I can tell. Maybe there are more, and I have collaborated with a good chunk of these people. So I think he has left. So it's a pleasure to dedicate this lecture to him, Ramki, as we all call him. His life in mathematics certainly fulfills the wisdom of the Upanishads. So let me begin with a discussion on that obelisk or Rosetta Stone that was on the front of my talk. Chiseled in 196 BCE, the Rosetta Stone is a proclamation in 3 different languages: hieroglyphics, Demotic, and Greek. So the top you see hieroglyphics, in the middle you see Demotic, and the bottom you see Greek. It was discovered in 1799 by the Napoleonic contingent when they invaded Egypt. So I guess invasions of countries have some good. As no one knew how to decipher hieroglyphics or Demotic, the presence of the Greek language enabled archaeologists to decode the script. So having knowledge of one script, namely Greek in this case, enabled the decipherment of the other 2 languages, the hieroglyphics. This is why now how we know what the hieroglyphics at least symbolize. So why did I mention the Rosetta Stone? Well, the analogy of the Rosetta Stone was invoked by Andre Weil in discussing certain themes in number theory. In 1921, Emil Artin discovered an analogy between function fields over finite fields, these are called global function fields, and algebraic number fields. And he developed a theory of quadratic function fields and was the first to conjecture that if you have an elliptic curve modulo p with p prime, then the number of points n sub p is p plus O of square root p. Now this conjecture of his was proved in 1933 by Hasse. And in 1939, Weil noticed a further analogy between the theory of Riemann surfaces and global function fields. So by 1941, he had a proof of the analog of the Riemann hypothesis for zeta functions of curves over finite fields. And it is this threefold analogy that led him to formulate his famous conjectures in 1949 that were later proved by Dwork, Grothendieck, and finally Deligne. So there was an analogy between number fields, algebraic number fields, and Dedekind zeta functions and Artin L series on one hand. Then there was an analogy to the function fields with the zeta functions of function fields over finite fields. And then there was an analogy to Riemann surfaces and the theory of curves. So these threefold worlds seem to be interconnected, and the Weil conjectures are a testimony that this interconnection is not just superficial, but extremely profound and deep. So the analogies between prime numbers and irreducible polynomials. So you take a finite field of Q elements, FQ, and look at the polynomial ring. And the analogy is that irreducible polynomials in this ring A and prime numbers in ordinary integers are analogous. and we can search for analogs of classical theorems in the function field case. So once you have set up this analogy or the metaphor of the analogy, you can now begin a program of research, and you could see what theorem in the number field world corresponds to what theorem in the function field world, and or you can go in the other direction. And so this is basically the theme that Arden had initiated. An explicit formula for the number of irreducible polynomials of degree n is quite easy to deduce, and we teach this often in algebra classes. The formula is given by this Mobius function, 1 over n summation d divides n mu d q to the n over d. So that's a very easy thing. And from this, it's easy to see that the number of irreducible polynomials of degree n is q to the n over n, and the error term is q to the n over 2 over n. So this is the analog of the prime number theorem with an error term as good as RH in the classical case. So with this very elementary observation, you see you have the kind of Riemann hypothesis in this trivial case. So now that we have set up the analogy, you can ask, well, are there function field analogs of classical theorems of prime numbers? So just like the prime number theorem has this analog, we can ask, is there an analog of Dirichlet's theorem of the infinitude of primes and arithmetic progressions? So, and indeed, this is a theorem, a famous theorem of Kornblum, 1919, a student of Edmund Landau. He proved it in his doctoral thesis. And after Kornblum died in World War I, Landau had the unpleasant task of writing up his thesis in the form of a paper which appeared in Matt Zeitschrift. So this is the problem with global conflicts. We lose intelligent people. So the theorem is as expected. So A of x and M of x are two co-prime polynomials, and the theorem is that there are infinitely many irreducible polynomials congruent to A of x modulo M of x. So we call that capital A's FQ of x. And if we want to do a counting of this number of irreducible polynomials in a given arithmetic progression with degree capital N, then you can write down using, again, an analogs of the theory of L series. The main term is q to the n over n with 1 over 5m, and this 5m is the analog of what you expect it to be. It's the number of coprime residue classes modulo m, the analog of the Euler function. So you have all this beautiful stuff emerging, and as you can see, you know, the classical theorem of Dirichlet in primes and arithmetic progressions goes back to something like 1860. And then we have Kornblum's theorem appearing in 1919. Now, the dth power residue symbol was introduced in Arden's doctoral thesis in 1921. Karlitz observed that the general reciprocity law for global function fields can be derived easily using basic Galois theory. So when you want to define the dth residue symbol, the d has to divide q minus 1. And we know that x to the a is a dth power is solvable if and only if a to the norm p minus 1 over 2 is congruent to 1 mod p. So this is a very elementary exercise. It applies generally to cyclic groups called the Euler criterion, which you probably know in elementary number theory. And the left-hand side of this congruence is in any case an element of order D. And since the mapping F goes to A mod PA is 1 to 1, there is a unique alpha such that A to the P minus 1 over D is congruent to alpha, and that's the dth power residue symbol. So now that I've defined the dth power residue symbol, we'd like to know if there's a reciprocity law, and the answer is yes. Suppose P and Q are irreducible polynomials of degree delta and nu. Then the q over p, the dth power residue symbol is equal to p over q modulo this plus or minus sign, which is given by this factor. And here's the remarkably simple proof due to Karlitz. Let's define A over P to be the Q minus 1th power residue symbol, and then any Dth power residue symbol will just be a power of the Q minus 1th power residue symbol. And so it suffices to prove it in the special case of the Q minus 1th power reciprocity law. And if you have a root of the polynomial p, remember p and q are irreducible monic polynomials, and the Galois automorphism, is just x goes to x to the q. That's it, and they're all cyclic extensions. Therefore, if you have one root, alpha, you have all the roots. They're given by alpha to the q squared, dot, dot, dot. So you can write down the polynomials in this neat, very clean fashion. And once you do that, I'm not going to go into all the details, but once you do that, you apply the Euler criterion and ask yourself, what is this q of t mod t minus alpha equal to? And you write this down in terms of q to the delta minus 1 over q minus 1, and then that as a sum, and then realize that this can be rewritten in this neat form. And then once you've done that, then you can write down the, because this has to correspond to the qth power residue symbol. When you evaluate it, it turns out to be this double product. And now you see a symmetry. Once you have the symmetry, immediately you see q over p and p over q are equal. Modulo a sign, you take care of what the sign is, and bingo, you get this remarkable d power reciprocity law. In the function field case, it's actually simple Galois theory and nothing more. In the number field case, it's more complicated than that. And most of you know it, you have to get into this theory of the Stickelberg element and things like that. So it's a little bit more complicated in the number field case, but in the function field case, it's very beautiful and very simple. An application of this is if you have a square-free polynomial of degree capital K, you may want to count how many irreducible polynomials are there such that a of x is an Lth power mod p of x. And I just want to present a neat application of this. The number of such polynomials is, I should have said something else. I should have said p of x has degree n, sorry. P of x is degree n. So how many such polynomials are there? N sub L is bounded by q to the n divided by L to the k, where k is the number of the degree of a of x. And the reason for this bound is if you factor a of x into irreducible polynomials and apply the reciprocity, it shows that p of x must belong to certain progressions mod a of x. And that means it must belong to these progressions. And then you just start counting how many polynomials are there in a given arithmetic progression. And the nice thing in the function field case as opposed to the number field case is you're essentially counting polynomials of a certain degree, and you don't have to worry about greatest integer functions and things like that. So that kind of gets wiped out. And so once you understand that, you get this remarkable clean bound. Sieve theory in the function field case is a little cleaner. An application of this idea is to the Artin primitive root conjecture in global function fields. On September 12th, 1927, so people keep remembering September 11th, I want to remember September 12th. September 12th is important for this Artin conjecture. Artin, in conversation with Hasse, formulated his famous primitive root conjecture. In this, he was motivated in showing a concrete application of his non-abelian L series. And he formulated, and as everyone knows, it's still an unsolved problem, although much progress has been made by many mathematicians. In 1933, looking for a thesis topic for his student Bill Hartz, Hasse assigned Artin's conjecture as a problem for research. A year later, Paul Erdős announced that he had a proof of Artin's conjecture modulo the generalized Riemann hypothesis. This discombobulated Bill Hartz completely, that Hasse had to find for him another research topic, even though Erdős's proof never appeared. So Bill Hartz worked on the function field analog of Artin's conjecture and solved it assuming the analog of the Riemann hypothesis for curves over finite fields. And he published his work in 1937. And in 1939, Davenport wrote a paper in which he noted that the full Riemann hypothesis is really not essential in the function field case, and a quasi-Riemann hypothesis suffices to solve Artin's conjecture in that case. This is not very well known, but anyway, the work of Davenport is beautiful. It's quite elementary, using only the theory of Gauss sums over finite fields. And the key theorem in his paper is that if f of x is a polynomial of degree k and chi is a non-trivial multiplicative character, then summation chi of f of x is equal to O of q to the 1 minus, what is that thing? 1 minus 3 over 2k plus 4. So whatever it is, the power is strictly less than 1, provided k is at least 4. And this was sufficient to resolve Artin's conjecture for a global function field and give an elementary proof without the use of any high-powered algebraic geometry. In a recent paper, my postdoc showing Kim and myself, we gave an even more elementary proof based on a classical idea of Hadamard and de la Valle-Poussin and their proof of the prime number theorem. Most of you know that the prime number theorem, the classical prime number theorem, relies on the fact of the non-vanishing of the Riemann zeta function on the line real part s equals 1. And then Hadamard noticed that you could do slightly better than that. You could actually get a tiny zero-free region for the Riemann zeta function that allows you to produce an error term. And our my joint work with Shoing shows that if you do the analogous calculation in the function field case, you do get a zero-free region, and that's essentially enough to solve Artin's conjecture in the function field case. So let's just give you a crash course in the theory of L functions over finite field. You have an R tuple of multiplicative characters, an R tuple of irreducible polynomials, and you can form these character sums, S of x. And then you define the resultant of two polynomials to be resultant of two polynomials f and g to be product of f of theta, where theta runs over the zeros of g. And then with this definition in hand, you can now define a character on the polynomials. X of g is a product of these characters. And then develop an L function. And it turns out the properties of the resultant are enough to show multiplicativity of the function x of g. And this L function not only is a Dirichlet series, but it also has an Euler product. So here's the basic setup. The Euler product is as you expect it to be. But because you have the Euler product, you can analyze the Euler product. And for example, in the simplest possible case, when you look at A equals FQ of X and you try to write down the zeta function corresponding to that, it turns out to be a very simple function. And from this particular zeta function, by the way, you can rederive that formula for A sub n, the number of irreducible polynomials of degree n that I mentioned at the outset. But now in this context, it has zeros, but poles at s equals 1 plus 2 pi I n over log q. So somewhat slightly different in sharp contrast to the classical case, because in the classical case, the Riemann zeta function only has a pole at s equals 1 and no other points in the complex plane. Now, the L function turns out to be a polynomial in q to the minus s. The reason for that is really the Euclidean algorithm, division algorithm. And so you can write down the L function in this fashion, where these things q to the si's are the roots. And so this is to be thought of as the analog of the Hadamard product factorization. It's very simple in this case, you see. Hadamard product factorization in the function field case is like this. And so if you understand your classical de la Valle-Poussin argument of finding a zero-free region, it's a play on the classic 3 plus 4 cos theta plus cos 2 theta being non-negative and the Hadamard product. So you end up getting this inequality, and then you get a zero-free region of the following shape, that the L function has no zeros to the right of 1 minus c over k minus 1 log q, where k is the sum of the degrees of all the fi's, and q, of course, is that. So c is an absolute constant. So you get this kind of zero-free region. Now, if f of d is the order of q mod d, here's an application. Let a of x be a square-free polynomial. The number of irreducible polynomials in fq of x of degree n for which a of x is a dth power is q to the n over n. We saw that in the counting of the irreducible polynomials, but now you have to divide by d f of d. And then there's an error term. The error term is O of q to the n e to the minus n over f of d times k. So this is the analog of the prime number theorem for this particular problem. The proportion of irreducible polynomials for which a of x is a dth power is given by this probability df 1 over df of d, and this is the error term. So now we can apply this knowledge to the Artin primitive root conjecture. So fix a parameter y, write q to the n minus 1 as a times b, where a is composed of primes L less than y and b is composed of primes bigger than or equal to y. I'm going to choose y later. And you don't need to really worry about too many of these technical details, but f of d then can be bounded as e to the cy. And by our theorem, the number, each character sum that corresponds to a non-trivial character is O of q to the n e to the minus n over f of d times k minus 1. And then choosing y to be very small, you can control the error. And so the final crux of the matter is the number of irreducible polynomials for which a of x is not a dth power for all d dividing capital A is by the inclusion-exclusion principle given by the sum. So this is kind of an elementary sieve. So we do the simple asymptotic sieve. So I've calculated already the number of irreducible polynomials for which a of x is not an nth power for all divisors of A. Now I have to, remember I factored q to the n minus 1 as capital A times capital B. I have to worry about these large prime divisors. And these large prime divisors, I'm just going to subtract those irreducible polynomials for which it is an nth power. And I split that sum into two pieces. And we'll apply the nth power reciprocity law to the last piece. Remember earlier, I gave you an estimate for n sub L. And now we choose the with this choice of z, and because of this rapid convergence with L bigger than z, you get an estimate like this. And then finally, the middle sum. In the middle sum, you actually apply that previous lemma 0.1 that I wrote down, and you end up getting this as an estimate. And notice that this is q to the n over n divided by L f of L, and L is bigger than y, and it's less than z. But the fact of the matter is that summation 1 over, so I'm going to choose z to be n to the 1 minus epsilon, summation 1 over d f of d actually converges by a famous theorem of Romanov, which is an elementary theorem, by the way. I don't want to get into proof of all that stuff. And so you end up getting finally that the an asymptotic formula, but now you have to analyze the main term. And in order to analyze the main term, there's a beautiful inequality of Heilbronn that we use. And this is says basically if you have x1 to xn real numbers with 0 less than xi less than 1, and a1 to an are finite set of natural numbers, then this inclusion-exclusion combination with the LCM of the AIs has a lower bound. And we apply that in our context, and lo and behold, the main term is big. We just need to show that the main term was big. And so the two error terms were small, the main term is big, and lo and behold, you get an elementary proof of the Artin conjecture over function fields without using any non-trivial quasi-Riemann hypothesis for the zeta functions over function fields. And in the time remaining, I think, I'm not sure how much time I have, but I think it's a 45-minute talk. So I thought I would conclude this talk by talking about an analog of a theorem of Mirsky. In 1949, Mirsky showed that every sufficiently large natural number can be written as a sum of a prime and a k-free number. And in 2001, Wei Chen Yao looked at the function field version of this paper and wrote a paper which he almost proved the analog in the function field case. Some errors in estimation were flagged by Mirel Carr's math review, and the problem appeared in Morey's 2012 survey paper on Artin's conjecture. And that's how I ended up noticing the problem. And Shoin Kim and I studied Yao's paper, and we noticed that the error in his paper can be fixed by a careful analytic method. So how do you correct it? So now we have the following theorem. If capital M is a fixed polynomial and k is at least 2, denote by p plus the set of all monic irreducible polynomials with degree d, such that p plus m is a k-free polynomial. Then you have that the number of such polynomials has a certain degree. A number of such polynomials has a certain density, and this density is given by this product. And then we can also derive not only an asymptotic formula, but an asymptotic formula with error term. And keep in mind, by the way, that the number of irreducible polynomials of degree d is q to the d over d. So this quantity q to the d over d is essentially the denominator. So you put that in, and then you get an error term here. And we need to use the analog of the Mobius function to sift out k-free elements. So again, this is what is going on here is we're using the analogy between classical number theory and function fields to transport some techniques. And it turns out that sometimes some of these techniques transport neatly and sometimes they don't. In this case, most of it transports neatly. Sifting and sieving in this process in the function field case is not too hard. And you have analogous functions, and sometimes there are actually no error terms. So here's the notation that we used in order to set up our thing. So I told you already, this capital A is FQ of T. A plus is a set of all monic polynomials, and P plus is a set of all monic irreducible polynomials in A. And then we have the definition of the classical analog of the classical Mobius function. Mu of Q is just going to be -1 to the R, where R is the number of distinct prime factors when Q is a square-free polynomial. And it's 0 otherwise. And we define a new function, mu sub k of q, which is going to be 1 if q is k-free and 0 otherwise. And then you can write down a formula for mu k of q in terms of the Mobius function. So this Mobius function should not be confused with the classical Mobius function. Here we're talking about this Mobius function here. We just use the same notation. So we can now set up the counting process. The general setup is that if you have, you want to count the number of irreducible polynomials, so P plus M is k-free. So this is what you would want to count. And then you rewrite your mu k in terms of the Mobius function I defined on the previous slide in this fashion. And then you split this sum. So here, degree of A to the k B. Keep in mind that the degree of P is growing. M is fixed. P is growing. Therefore, if you take the kth power of a particular polynomial and multiply it by B, then you can see that the degree of A has to be, if the degree of P is D, you will see immediately the degree of A has to be bounded by D over K. So you can write this, rearrange the sum in this fashion. And now the inside sum, you're counting the number of irreducible polynomials of degree D such that P plus M is A to the KB, and A is now fixed outside. And the beautiful thing is that inside you can use Kornblum's theorem. See, you're counting primes in a certain arithmetic progression, mod A to the K. So but before we do that, this is what Wei-Chen Yao actually did. But his mistake was he tried to analyze the whole thing at one go without being careful about errors. In one place, the error calculation turns out to be wrong, but the strategy that he had is sound. And so anyway, we do that very carefully. We have to break it up a little bit more carefully than he did, and then but it ends up working. So for any t, you can decompose this sum into two pieces: t less than or equal to d over k, and t. And so the degree of A is less than T and the degree of A is bigger than T. That's what I'm saying here. And then once having done that in the first part, you have to apply Kornblum's theorem. So Kornblum's theorem, as I mentioned earlier in an earlier slide, it's Q to the D over D with a 1 over 5Q, but there's an error term and the error term is bounded in this fashion. And notice that this is a minus sign here and this is a plus sign. So it's basically bounded by this stuff. And so you can put that in and then calculate the error. And then you have to worry about the second term. So the estimates come out rather neatly. I'm going to skip all the details. You understand the strategy. So you end up getting a main term and a particular error term. So this is the case when the degree of A is less than or equal to T. And notice that the main term is of size Q to the D. So Q to the D. So you plug that. This is the main term from each of the inner parts. You shove it in. And so when you do that, you end up getting the following. For the error for the second term, we have to analyze the second term. Second term, you have you apply actually a trivial estimate. So you just put absolute values on mu of A and apply a trivial estimate. You end up getting d k minus degree of A, and then lo and behold, you get that. So now one needs to analyze the tails, and these tails are tails of actually. Sorry, this is a convergent series, but keep in mind that this is a summation over A, so the degree of A is bigger than T, so the tail of a convergent series. And when you analyze that very carefully, you end up getting this kind of stuff was not done in Wei Chen Yao's paper. So finally, we end up getting the main error term is in this fashion, and the main term is of this shape. And once you analyze the multiplicativity, exploit the multiplicativity of these terms, you would like to. It's a finite sum, but now you'd like to analyze this main term, and you'd like to take it all the way to infinity, so that you can write down this thing as an Euler product. But then you have to calculate the tail again, and that's not hard to do. The main term is easily analyzed. You extend it to infinity, and you can write it as an Euler product, which we do. And then you have to calculate the tail, and the tail turns out to be easily calculable. And the error term is of the same size as before, and this completes more or less the proof of the theorem. So that's basically the idea behind these two theorems. So as I've tried to mention, the worlds of number fields, function fields, and Riemann surfaces, the analogies that exist between them can be exploited, and one could now take problems which are existing in the number field world and ask what about the function field world. You can also go backwards and ask what about problems in the number field world given a result in the function field world, and use this as a theme and program for research, and also to expand your understanding. So thank you very much for your attention, and happy 60th birthday, Ramki, and many more happy returns. And once I'm back in India, I want to treat you at my tea shop. Okay, so there we go. Now that was not Photoshop. There is an actual tea shop there that was like that.
Because the spelling is suspicious. That's what.
No, the
generally-
spelling is. No, I know they usually put an H. They usually put an H, but this is
Yes,
this
yeah,
is somebody
yeah,
has
what-
some tea shop owner has the same name as I do.
Exactly. Yeah.
So that's our next order of business. Find out where this thing is.
But you know where you took the picture, right? You might have taken the picture. It was in Chennai, or
No, I didn't take the picture. I didn't take the picture. I actually found it. No, I found it on, yeah, it's in Chennai, but I found it on Google. So should I stop sharing? Is that? Yeah.
Thank you very much, sir. So anybody have any questions or comments?
You said the quasi-Riemann hypothesis, Davenport's result about quasi-Riemann hypothesis implying primitive root conjecture. So similar kind of implication you would expect also in the case of number field, or in the general case of integers.
Well, in the number field case, in the number field case, the Artin primitive root conjecture was solved by wholly assuming the generalized Riemann hypothesis.
Yes.
Hmm?
Yeah.
And then there's a considerable amount of work of myself and
Yes.
others in this context, and where we showed that one of a finite set of numbers is
Yes.
many primes, right? We showed that.
Yes.
Yeah.
Yes.
So now your question is it possible? I'm getting some feedback. Is there a problem with the? Can you
Sorry,
hear me?
it could be from me because both me and Purushottam are here. It could be that.
No, we can hear properly.
Okay. Anyway, so now it seems to be okay. So I think if I understand your question, this is what you're asking. You're asking, now that we know the Artin primitive root conjecture in the function field case in a very simple sort of way, is it possible to transport some of these ideas back into the classical case and get something new? That's your question, right?
No, I do not expect to get a better result by these techniques in the in the case of integers, but I was hoping that is it the result of Davenport? Corresponding results are already known. I mean, Woolley's result is by using Riemann hypothesis, generalized Riemann hypothesis, but corresponding to Davenport, is there a result? No,
That's a good question. So yeah, I know. So I'm trying to rephrase
not your
it.
result. Your result is much stronger.
Yeah, so your question is basically, is there something known about Artin's primitive root conjecture, assuming just a quasi-Riemann hypothesis?
Yes.
Yeah, that's a very good question. And I believe, I believe that I had, I think one of Balu's students, Amora, I gave that kind of thing as a problem. And so you could prove that if there are no zeros to the right of some number, I forgot what it was, but some, then you can actually get Artin's conjecture. But what is interesting is, your question is, will any quasi-Riemann hypothesis do, or do you need some number there? And at the moment, the state of knowledge seems to be you need some number there, but I am convinced, good research problem, I'm convinced that a quasi-Riemann hypothesis will do. If you only want to prove infinitude.
Yes.
Not forget asymptotic formalism.
No,
If you want to prove there are infinitely many primes, I suspect that a quasi-Riemann hypothesis would be sufficient.
And in your proof, you make this finiteness avoiding Riemann hypothesis. The techniques are to avoid generalized Riemann hypothesis.
Yeah.
But can that be now modified if you know quasi-Riemann hypothesis can give you? Can it be can you make it finer? Does it? Is it a possibility?
That's a good question. So the way we avoid the Riemann hypothesis is by using sieve theory.
Yeah. Yes.
So your question then is it possible to marry sieve theory somehow into some sort of quasi and get better results? And I sounds good. Sounds like a good plan to me.
Okay, that's sorry. Okay, I'll leave it.
Sounds like a good plan, and I have a suspicion it's probably true. You see, so coming back to your other question, whether or not the methodology that was used by us, now that we have a very super simple proof of the Artin conjecture in the function field case, the two punchlines there are a simple asymptotic sieve and the reciprocity law. So the question then becomes, is it possible to somehow inject the higher reciprocity laws into the Artin primitive root conjecture? As far as I know, no one's been able to do that. And that has been a subliminal thought in my life. Haven't figured out exactly how the my suspicion is that somehow the Stickelberger theorem about the factoring of the Gauss sums and the higher reciprocity laws can probably be used, and it is probably worth one's while. I see a lot of youngsters in this room, in this virtual room, so I suspect that if you study that, I mean, it's worth studying just for its pure beauty. Study the higher reciprocity laws and see what, try to understand it. Forget trying to prove any theorem, just try to understand it. And I suspect that something should come out.
Thank you.
Yeah. Did I end early, Purushottam?
A little bit, yeah.
Okay. Was it a 45-minute talk?
Yes, it was.
Okay, good. Oh, I'm on time.
Ram, can I ask a question?
Absolutely.
Are there
Hello,
analogs
Rajan.
of, Rajan. Yeah, very nice. Yeah. Are there analogs of the Goldbach conjecture or the twin prime kind of conjecture? You fix a polynomial or some such thing, and look at
Yeah.
polynomial, right? Are there analogs of that?
There are. Yeah.
And they
Now
are
this
known
is
to be true.
Yeah. So this is a good question. This is really a good question, and this is where I think I have people like myself. I'm getting feedback again. I don't know. Rajan, do you want to turn? Yeah. Okay. So I suspect that if this is where somehow you have to kind of discard your classical number theory perspective and just dive in. It turns out that these questions, as you ask very nicely, were investigated by Hayes and Effinger and Hayes in a book, which I have a PDF copy of, but can't say I've read. You see, the curse of modern technology is I have PDF copies of lots of books I haven't read. So this is one of them. And interestingly enough, there are problems that are unforeseen that show up. Though it's on first glance, it looks as if it should be doable, like the Goldbach conjecture or the twin prime. These are actually being looked at. I can't say I'm the super expert on this. Maybe somebody here is an expert, but it seems to me the analogs go through, and if I'm not mistaken, for example, the Goldbach conjecture is still unsolved in the function field case. I have to check that, but that's what I got the impression from Heffinger and Hayes. So maybe somebody in the room knows more about the status in the function field case, but I think it's not so simple, and there are new problems emerge. New problems seem to emerge, which are surprises, especially from an algebraic geometric perspective.
Wow, okay. Also, this that problem of Hardy or somebody, this n squared plus 1, there are is that what infinitely many primes of the form n squared plus 1? No, what is that?
Yeah, that's a problem. I'm not sure if it's Hardy and Littlewood, but it sounds right to me. Sounds like polynomial values, polynomials assuming primes infinitely often sounds like a Hardy-Littlewood conjecture to me.
Yeah.
And I believe they made that conjecture using the circle method as the model, and then they made, so then the question is, as you correctly asked, what is the function field version of that, and is that known? And I have to confess, I didn't do my homework. I don't know the status of all those things. But fortunately, there are lots of youngsters in this place. This is something that you could just sit down with a notebook, one of these famous Ramanujan style notebooks. You sit down, go to the library, find out what's known.
Ram, you look younger than the rest of us, and you seem to have more energy than us. I'm sure you would do it before us. You don't know already the answer.
No, I see Biplab, I see Rashi, I see Jyotsna, I see all these people. So I'm addressing my comments to them.
Oh, I see Balu also.
Well, there's a good book I can recommend. Arithmetic of Function Fields by Michael Rosen.
Oh, okay.
And it's a beautiful book. It's a book that all the youngsters can read. The only problem is that he reproduces Bilhartz's complicated proof of the Artin primitive root conjecture in function fields. So I'm sure that if he had our proof, he would have shoved it in, and you would have had a better treatment of it. So I consider our work to be now textbook material. So it should get into some book like this. I don't know what you think.
But could I just make a comment on the question that Rajan and others were asking?
Yeah.
So besides the function field case, in these more subtler questions, there are new aspects that don't appear in the number field case, and one of them, Ram has already mentioned it, is that the Mobius function, which is key to doing any kind of sieving, turns out to be a character. And that is kind of critical. It's been exploited in several recent papers. So we've got an extra tool that you don't have in the number field. It's not Riemann hypothesis. It's something different. And so that so that could be crucial in these kind of subtler problems of distribution and analogs of problems on distributions of primes or sequences with certain divisibility properties.
Yeah, actually, you're right. You know, there's this Rajan, I think you know, for example, the famous conjecture of Chawla. You know, Chawla with the Mobius function. He was, and it goes back to this Sarnak's Mobius randomness business. So the idea is that the shifts of the values of the Mobius function should be independent. So the beautiful question of Chawla was, you know, the prime number theorem is equivalent to the fact that summation mu of n is little o of x. Summation n less than x mu of n is little o. And then he asked, well, let's generalize the prime number theorem by saying mu of n plus 1, mu of n plus 2, mu of n plus 3, dot, 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 mu of n plus k, let's say, shifts. And can you show that these sums are also small? And we don't know the answer to that. But in the function field case, in the function field analog of that has been solved by a bunch of people. The name Schusterman seems to come into my head, but I think there are other authors in that paper, but that's the name that seems to come into my head. It's been proved. This conjecture has been proved now in the function field case, and the reason for that is exactly what Kumar is saying. The Mobius function turns out to be a character. You know, it's actually elementary to prove that Mobius function is a character. I mean, I think I gave a mini course in ISER. Where was that? ISER, IIT Gandhinagar, I think. Must have been, I think. I gave a mini course on this function field stuff, and I think I did mention this, that the Mobius function turns out to be a character in the function field case. And so when you're talking about averages, and now you can see, when you talk about if mu of n is a character, the Chawla problem becomes a kind of like an Andre Weil type estimate because it's a character sum of a polynomial.
Okay.
You get the idea. I mean,
yeah. Okay. Once it's a character, you are already talking about the character sums, chi of f. Yeah.
And you know, the other thing that I have to mention is Weil2. You see, Weil2 is essential in all of this stuff.
Okay.
And by the way, the construction of the Hasse-Weil zeta function, the construction of the Hasse-Weil zeta function is motivated by algebraic topology. You see, and what I find fascinating is you have an elliptic curve and you have an elliptic surface, and somehow all these APs, when you average them over a surface, there's a remarkable cancellation. So this idea of Weil-Lang, you know, fibering varieties and getting estimates is no good, in the sense that it falls short of the optimal error term. And so you really need to interpret this as a zeta function of a surface, and then use Weil2, that the Riemann hypothesis is known to say that there's lots of cancellation. Oh, beautiful stuff. There's all, and I think that's the punchline in the Schusterman and others paper.
Wow. Okay. Very interesting. When did this appear? Long back or
maybe a year ago? A year ago or 2 years.
Okay.
I mean, I was carrying it.
Ram, the other one is Savin.
Oh, Savin. Yes, thank you. Yeah. Srinu, yeah, thank you, Srini. Yeah, Schusterman and Savin. That's right.
Okay.
There may be other authors. I kind of vaguely remember that. But you see, this is the problem. The curse of the modern technology is you accumulate lots of papers that you have to read and end up reading nothing. So this is why we need many lives, see?
You keep doing something that is better than reading. I don't know.
Can I ask a question?
May I ask?
Go ahead.
Go ahead, please go ahead.
Hello, can you hear me?
Yes, yes, we can
Yeah.
see it. Please go ahead.
Yeah, Professor Ram, this is Ramesh.
Hi, Ramesh.
Yeah, hi. I just have a very general question that, is there any study in the past on primitive root being prime, on prime primitive roots, or are there any instances where you have seen any interesting application of prime primitive roots?
You mean in the classical context?
Yeah, in the classical context, yes.
Well, I think it's an interesting question, and I don't see how the problem becomes any easier by imposing that the thing is prime. Although I don't want to say that outright, because in a sense, in the function field case, I was looking at a of x being a primitive root, right? I mean, that's so a of x was a polynomial. In the function field case, the factors of a of x show up and do have a role to play. So that's an interesting question you asked. In the function field case, the number of prime factors of a of x does matter, but in the number field case, as far as I can tell, it doesn't seem to matter. As far as I can tell, but it's an interesting idea. It goes back to this business of trying to figure out how to use Stickelberger's theorem and the Artin primitive root conjecture again.
Okay.
Does that help?
Yeah, sure. Thank you.
I thought somebody else had a question. Shauli, did you have a question?
Yes, sir. May I ask?
Yeah,
Sure.
Yes, sir. You said that Mobius function can be viewed as a character. So, so which type of character it could be, and what will be the conductors, something like that?
It turns out to be it's a quadratic character. I mean, it's actually elementary to prove this. I forgot who proved it, but it goes back to the 19th century. I mean, if you reinterpret it correctly, it goes back to the 19th century. And I think I may even have it in my notes in the IIT Gandhinagar lectures.
Okay, so I will see it.
Yeah, it's an elementary. Were you there for that course?
No, sir, I was not there.
Your voice sounds familiar to me.
Yes, sir, I'm sort of.
Okay. Yeah. Oh, hi. Yeah.
I did PhD from TI for Mumbai under some.
Oh yeah, I remember that. That's right. I remember that. And I think you helped me get to the airport one time too.
Yes, sir. Yes, sir. Yes.
Okay, anybody else have any questions? If not, let's thank both the speakers of the final session. Thank you very much. If the organizers have anything to say, otherwise, please go ahead. Please take over.
Thank you.